Okay, we're ready to start, everybody. Let me turn on everything now too. Okay, can you see me, everybody?
Yes, sir.
Good. I'm setting things up here. There we go. Okay, let's get going. I hope all of you virtual are feeling okay, or if you're positive or whatever else. I see we have 12 people online. Good. So what I'm going to do now is continue with the book, but I was commenting to the other students here while I was setting things up. I had to go run and get the adapter, so that got things delayed. But basically, I was very pleased with how well everyone did on the last quiz, even though it was kind of like take pictures of it, et cetera else. So it's clearly you're getting the stuff. And believe it or not, this next test is one of the easiest of the semester, okay? If you practice enough, okay? Because there's really no math really other than plugging in the equations. And based on what I've seen with you handling the math, you're pretty good at that. So basically, and you will be given a periodic table with all the equations on the back, as well as is going to be in the sheet for the test. So believe it or not, we're not really worried about it. That's why I say also for the first part of the thing, basically I like to drop one of the first tests because what I want people to know is what they know at the end of the semester. And I don't know whether it'll be the first or the second, but I plan to minimize it, but you have to justify it by doing well on the next two tests and the final. Okay, yes?
Can you just drop the lowest test grade?
I hope. I'm going to talk with the chairman to work it out because he didn't really want me to do that. But because of the semester and the nature of it, then maybe I got more justification. Yes? Yes? Okay. Yeah, and the equations. Okay. And you'll have the 3x5 card. So you just have to practice enough. That's it. Yes. A week. Yes, it'll be either Monday night, next Monday, or next Wednesday, depending on how much I cover this week. But basically, we're just going to finish this chapter and then essentially do a little bit more of molecules in the next chapter, be on the next test. But I'm going to cover Lewis dot structures and the basics of hybrid orbitals, and that'll be on the exam. Yeah. Yes. Yes. So even if you're in a low category, and if I drop one of them, and I'm gonna go on your behalf to drop one of them, that you're all on behalf of getting C or above based on how hard you work. So I do want to encourage you, those who are remaining in it. But if you're getting more and more lost, it's better to drop the class and then take it another semester where you're not as cluttered with this COVID crap and half hybrid, whatever. Yes. Go ahead. No, that's all right. If it's important, you'll remember it eventually. So that's any of you at home have any questions? If anybody wants to see me for my office hours today, because I'm going to be grading your quizzes as well as the lab exams, primarily in my home on my dining room table, so that I don't have any distractions. I'll be working all afternoon on that. Basically, I'll do any office hours at 12 to 15 virtual today. So unless somebody needs to see me in my office. Yes. No, I think that there's a schedule set up, and I don't know whether it's been posted yet or not. You could check the registrar's office to see if there's a posting, but it has something to do with 10 o'clock Monday, Wednesday, Friday, or Monday, Wednesday, Thursday would be at a certain time and place, and I don't know. And that's the way it traditionally works, huh? What day?
It's on the PC website.
Do you know what day it is? Have you, okay, the 24th, so that's Tuesday, correct?
Yep.
Okay, good, okay.
Online,
What?
our final exam's online.
No, I don't think so, because it'll be all multiple choice.
I thought with that, we have to go home. The dorm's closed on the 23rd. Like, we'll be at home.
That's odd. That doesn't make any sense. They couldn't have a final,
Look at it,
because there's a final, there's 4 or 5 days for the finals.
and like, the dorm halls closed on the 23rd. Like, that's the last day that we can be.
Yeah, they, on the 25th, right. And the last day of exams is the 24th or the 25th.
I don't know, that might be wrong.
No, I can't imagine that, because I don't know how we could do it online, because too many people could cheat or whatever else and things. It's not set up that way. Even though it'll be all multiple choice, that's part of why you're getting multiple choice questions in the thing to practice for the exam. Okay, so now, do any of you on virtual, do you have any questions of me? A bunch of students had questions here. Anyone there? Anyone distant have questions? Okay, yeah, go ahead.
Are we allowed to use flashcards on the next exam still?
No, you'll be able to use a 3x5 card, and you'll have the periodic table with a whole bunch of equations on the back too.
Okay, thank you.
No flashcards. But I would not recommend memorizing this stuff for this next thing. You just got to practice working the problems in the book. In chapter 10 of Hein, the Intro to General Organic and Biochemistry gives enough background and goes a little bit more into the basis of it, more simple questions, and then use both if you need to. But you really need to read the chapters. And it'll be chapters 5, 6, and 7 on the exam, so all the way up to hybrid orbitals, okay? And then a little bit more after will be on the next exam. So any other questions, those of you distant? Okay, let's start. What I'm going to do now is open up the PowerPoint, the next one on the list, and we'll get moving. Nope, wrong one there. I'll check the other one just a moment.
Dr. Douglas, what PowerPoint are we out of today?
What?
What PowerPoint are we using today?
We're using the one that's Chang chapter 9. Talking about chemical bonding. And it is chapter 7 in our book. They reorder the chapters there. So basically here regarding this. So basically we're going to talk about bonding and how that works regarding the thing. But what I want to do first is use the other thing here. I'll open up another one just so we get the other one for chapter 6. And introduce it, because they introduce it at the end of bonding theory of the chapter 6 here. Oops, wrong one. Okay, good. We'll just do that. We won't be using that. Okay, so what we want to do now is talk about chemical bonding, and I'm going to share the screen with you all and start this. So okay, can everybody see the screen? Those of you distant, can you see the screen?
Yes,
we can.
Okay, wonderful. Okay, now chemical bonding, and I'm going to draw on this screen just so you can understand where we're going with this. But let me make sure this is recording. Hold on a minute. I just want to make sure we're recording here. Okay, we are recording. Okay, my apologies. We'll go back to this slide again. Okay, now we were talking about chemical bonding, and we were kind of introducing the topic before with the sodium. Oops. Okay, first thing with the sodium, what is the electron configuration for sodium? And we can use the extended one, and in chapter 10 and 11 of Hein, there's some really good things for that. So what is the electron configuration for sodium? And we can use the abbreviated form. What are you going to have? Ne, yes. Okay, so it's Ne. You start with that, and then you have the 3s1. Okay, and then say for fluorine, this is essentially the next one, but it's 2s2, 2p5. Okay, 1s2, 2s2, 2p5. Now, what happens when the sodium goes to sodium plus? What happens to it? Goes to sodium plus 1. Huh? Yes, it loses, which one? Yeah, the 3s1. And that goes down there and then makes that 2p6. Okay? So now this is pretending to be neon, just like the other one. So now that's F minus. Now, what's the charge difference between both of them? What's the charge difference between both of them? Yeah, and this is +1 and this is -1. So what's the charge difference? No. 2. Yeah, very good. Okay, so you got the first one, which is called ionic bond. I don't know what's happening to this slide. For some reason, it's hard to write on it. Okay, but basically this is what you have is what's called an ionic bond, where it involves the exchange of electrons. Okay, you got the exchange of electrons occurring there. Okay, so how are they exchanged? Be practical here. How are they exchanged? What gives up an electron? Andy, what gives up an electron? No. Which atom gives up in the top part of the slide? Which one gives up an electron? Yeah, sodium. Okay. Which one gains it? The fluorine. Okay. They're both happy now. They both have the thing fitting the octet rule. Okay. So they're both happy. They're now in a thing. So you now have ionic bond between them. So that's the first part that's involved with this. Wait a minute. I'm trying to, for some reason this, I'm not able, hold on a minute, I'm not able to do this. I'm trying to get the PowerPoint to work properly. For some reason, it's not working properly for me to do this. Just a minute. Oh, okay, now it seems to be working. Now I'll share the screen again. It was putting a lag in there. Okay, folks, I'm going to share the screen again. I was having problems with the other one. Okay, let's do this now. Okay, we got the thing here. The valence electrons are the ones involved in bonding. They are the ns2, np up 1 through 6. Okay, they're the outside ones. Okay, so basically those are the ones that participate in chemical bonding. Usually the d orbitals and the f orbitals don't. Okay, there's only in special cases when they do, when they're empty. But practically the electrons in them don't get involved unless they're empty and make kind of hybrid orbitals or special orbitals, which we'll discuss a little later in this chapter. But the key thing is the valence electrons, okay? And when you have one s, you have one s1, two ns2, 2a, the number of valence electrons, 3, 4, 5, 6, 7, and then 8. Now, what I'd like you to do with this is that if you have a handy periodic table, particularly those of you at home, please take out one of the periodic tables from your backpack that I gave you. Okay, and what we're going to do is write on it a little bit. The periodic table I gave you, the simple one. How many do not have one? You don't have one? Okay, yeah, please give her the extra. Okay, I'd like you all to have one, or I can get more in my office, but I forgot to bring them. So what I'd like you to do over the top and use this periodic table when you're working your problems is put x dot, x here, dot, here, x with 3 around them, then 4, then 5, and spread them out. Why do we spread them out? Why are we spreading them out? Be logical. Sorry? Yeah, so they basically will spread out as far apart as possible from one another, okay? That's the key thing. So basically, if you set it up like this. Now, when I was a kid, I grew up with what are called Tinker Toys. Does anybody know what they are? What are they, Paige? Sort of, but they got like a ring thing which is made of wood with wooden sticks, and you plug them in the holes and build things with them. They're called Tinker Toys, but they're really cool. You can make big scaffolds of buildings or whatever else. I played with that when I was little. But believe it or not, the old style stuff for kids is better than the new crap. But the point is, again, it's a situation where if you understand the post goes in the hole and such like that, that's like forming a bond, okay? So, say for example, you have something like this, and this refers to NS1, NS2, etc., going across all the way to NS2, NP6, and then this is full. So basically you go all the way across and then 5 and then 6 there, but this is representing the things there. And if you look at all these here, they put all the dots around the individual elements. Why did I put them at the top? Because the rest just clutters it up, okay? Basically, you put them at the top and you can get the different things related to that, okay? So, again, you will keep this written on periodic table. Now, when you have the test coming up, I'll give you the periodic table, and I've had many students write the things across the top immediately, and then they're asked to draw a Lewis dot structure for something. Well, it's easy to do it then, okay? So basically, the Lewis dot symbols, building a Lewis dot structures is kind of what is illustrated in bonding. So if you've got something like this that is sodium with 1, and the fluorine, how many does it have around it? 7. 1, 2, 3, 4, 5, 6, 7. These dots are representing, what do these dots represent? What does a dot equal? Yeah, very good. So you get a little arrow on this, and the arrow goes like that. So what do you have there? Well, you have sodium now with a +1 next to it. Then you have the fluorine, which now has 8 around it. And this is -1. This charge difference, this holds it together, and this is called an ionic bond. Does everybody see how that works? And again, I've asked my students to do this, and so many of them mess up, they miss the point. What is this little arrow showing here? The electron transfer, very good. And those of you who are taking organic, you're gonna have all sorts of arrows in things because they all involve, moving those arrows involve the moving of electrons along the organic chain or something, okay? So the moving electrons is very important. What is the moving electrons called in physics and other things? Andy, what's the moving electrons called? No. What is just the moving electrons called? Anybody who likes physics, what is it? The moving electrons. It is called what? No, keep it simple. The moving electrons is electricity. It is essentially current, okay? So basically, this is connected. There's sort of a current. When you got exchange of electrons, you have a current. That's how a battery works. And we'll talk about batteries in general chemistry too, okay? And I'm teaching 2 sections of Gen Chem 2 next semester, okay? And I have a lot of fun with my students in Gen Chem 2 because those are the ones that have survived Gen Chem 1 and learned a lot by the end of the semester, and then they're all ready to go. So we get into really some good stuff with that. But the key thing to understand about this is essentially developing what's first called the ionic bond. Okay, and this is the first main kind of bonding that occurs. Ionic bond is electrostatic force that holds ion together in an ionic compound. So you got this one, Na+, and then fluorine minus, and always put in the dots around it. Why are there 8 electrons around the fluorine? Around the fluoride, why are there 8 electrons around it? Because it's now pretending to be neon, okay? So you always, when you have the ions, you always put all the electrons around it that are on the valence shell because they're the ones that have essentially absorbed those. And each of those pairs represent orbits that are now filled with them. And there are 3 orbits associated with this. There's one S orbit and then 3 P's orbits. And we already know what the shape is. You got the spheres, and then you got the 3 different structures like this, dot, 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 with that one out there. So basically, these are all filled up now with the fluorine. That's the 8. Each of these, there's 2 in the S shell there, there's 2 in this one, there's 2 in that one, and there's 2 in that one, making a 3-dimensional structure. How many electrons are in there? 8. They're both happy, they're both full, okay? Now, general question, calcium is +2, and oxygen, what would that be? Well, you have 6 around it, and so essentially you've got 2 electrons around calcium. What's gonna happen there? Yes, very good. So essentially use the arrows, boing, boing, okay? That illustrates the exchange. I put sound effects in there too, okay? But then now you have calcium +2 and fluorine, no, oxygen, which is now -2, okay? And so now be logical here. Which is the strongest bond? Between sodium and fluorine or between calcium and oxygen? Why?
Higher charge.
Yeah, the higher charge difference is a 4 charge difference between it. And that's called ionic bond strength. but it's a really very simple process, simple
Wait,
concept. You have a
Dr. Douglas.
+3 and a -3, you get that. Someone have a question?
Yes, so which one is stronger?
Well, what do you think? Which one is stronger, with a +2 difference or a +4 difference?
+2 difference? I mean, +4 difference, I'm sorry.
+4 differences. And essentially that's the voltage. The voltage is the potential difference between two point sources. So even the whole concept of voltage comes in here, and all of you have heard of voltage in some context, okay? But the point is the potential charge difference. When the potential charge difference is bigger, it's a higher voltage. Same thing with here, when you have calcium oxide or even magnesium oxide. Magnesium is the same thing, +2, and then oxide has 6 around it, 2 there. And basically this would be a 4 charge difference between them. Yeah.
Does it matter where we put the dot specifically? If we just show where they're going?
No, I would just, no, not really, but I would just spread them out, just keep them spread out, but put the arrows in there, then you'll understand it a little bit better. Because on the quizzes, when I did the quiz and tests of all the way back to Gen Chem 1, when I taught this the first time, basically, I keep asking people, put the arrows in there, and they keep forgetting, but the arrow, there's a point for it. Particularly if you go into organic, you'll understand it. Now I'm gonna get rid of my bad handwriting now. And
Wait, what are the arrows for? Like, but the arrows like going from one valence electron going to like the oxygen?
correct. And let me show you again with this. You got a okay, we'll go with the lithium. You got a lithium there with the fluorine. Okay, where's the arrow gonna go? Who's the one that, Brandon, did you ask that?
Yes, sir. It's gonna
Where's the arrow
go.
gonna go?
It's gonna go to the fluorine,
From where? Where's it gonna start?
the lithium,
Yeah, where?
where their valence electron is.
Yeah, on the dot. So essentially you put, and unfortunately these slides don't do it, but I've had to always write it in there, but I wish they would in the slide, but I'm not the author of the slides. But you essentially put that arrow in there, and that shows where the electron is shifting from. But what I would do it is, I would do it this way, just so it's easier to see. Li with this, and then the fluorine orients near it like this, and then you got the exchange of electron there, and then you end up with the plus, and then the minus on the other side. Does everybody see that? Yes.
So before the electron transfer, you don't put the charges.
Right, because they're neutral. Right? Because with lithium you have 3 protons, and so there are 3 electrons. So before you move it, it'll be there. Okay. Okay. Now let me remove my bad handwriting, and we'll go back to the thing there. Okay. So I'll put it back on there again. There. So essentially we go there, and now look at this one. That's 1s2, 2s1. And then 1s2, 2p5, and you got the combination of both related to them both. Now, the thing that's great about Hein is, for example, it does things in boxes like this here, illustrated another way. You have a box. This is the 1s2, and so there's a box there. And then 2s1 like this, 2s1, 1s2, and then you got 1 electron going up and then down, and then another up like that. And then the fluorine on the other side has 7 around it. So basically here you have the 1s2 over here for fluorine, that's full. And then you have 3 orbitals here, 3, 1, 2, 3 like this. And you got 1 going up like that, down, up like that, and down like that. And there's also another one, 1s2, and then 2s2 here. This is 2s2. And then this one is 1 up, and then this is empty. So what's going to happen with this is when you have the boxes, you can shift this electron will go over here and fill this up. Now this is full and this is empty. So now you've got, this one has a box like this. It's a happy camper. And then this one is full and it's happy for the same thing. So that's another way with the boxes. And that's why I recommend you go to Hein and look at it, because some students have found it easier to do it that way instead of the other way with the Lewis dot structures as an intermediate step. Yes?
Would both of those be on the test? Or
On the test,
Lewis dot structure?
the Lewis dot structure will be, but not the boxes. I just want you to practice just so you understand the concept. But I will ask you to put the arrows on it. Okay? Because what do the arrows represent?
The electron.
Yeah, the electron transfer, the movement of the electron, okay? So essentially you're trying to get that movement. Okay, so now we continue with this there, and you got a neon there associated with this. So essentially the lithium has lost an electron. This is the one that's lost. And this is a little hard to understand, but I like putting the arrow in, I like putting the arrow in here. So it goes like this, and then you got the arrow going in, that electron going in there, resulting with the whole thing over on the other side. And let me delete the stuff on the slide again. That's a bad error thing there. This arrow goes here like this, there, and then you've got it all like that. But people like to do it with breaking it off, and then you have the electron go in here. And I think the arrow gives a better visual representation than two lines of an equation, okay? Because again, understanding the flow of electrons, and again, as I said, I really love teaching organic, and the flow of electrons is very, very important in organic. And it's even important in biochemistry too, because that's how our body functions. And that's why we have a nervous system, okay? So, and that's why we need salt in our diet and everything else, because it's all about electricity in our body too, having the nerves work properly, okay? So it's really kind of cool how this all fits together. The lattice energy is essentially the energy required to separate 1 mole of a solid compound into gaseous ions. So if you got sodium fluoride and you have magnesium oxide, what is going to have a greater lattice energy? The lattice energy is the energy required to break it up. In other words, if you have a piece of paper and you could tear it up, it requires energy for you to tear up the piece of paper. Same thing here. When you're breaking up a compound, it involves breaking those bonds and tearing them apart from one another. Which has a stronger lattice energy, sodium fluoride or magnesium oxide?
Magnesium oxide.
Yes, very good, Brandon and Nick. Okay. And it's because the charge difference is thing. Now let's look at another example. How about aluminum nitride, which has a stronger bond? Aluminum nitride, why? Because the charge difference is 6. Now, the rest of this slide is going to get into numbers, okay? And you don't have to concern yourself with numbers other than using the equation. So essentially, I'm going to erase the slide and go back to them, but it's important to understand what's happening when you have the numbers, because this is what chemists do when they're doing the experiments, is trying to determine how much energy this is. So let's look at this. The energy here is on this. E is the potential energy. This is the potential energy, okay? That's the charge difference. That's the voltage difference, okay? Q plus is the one for the plus ion, like sodium plus. The Q minus is the chlorine minus, okay? The R is what? What's the R? That's the radius. So if you got a sodium chloride set, the radius is going to be the distance between the center of this and the center of that. So this is the R there. So of course the energy is related to that R, because if you're going to separate them, you essentially are based on how far away the thing is being gripped. Now, what's easier to pull away from a friend if they're holding a textbook close to their body or they're holding it out like this? Holding it out is easier, okay, because it's just with the hand. But if you're holding it tight like that, the closer to the nucleus, it's harder to pull it away. So basically, when there's a bigger charge difference, and that's what the sodium that's what the aluminum +3 would be. Like in this case, aluminum nitride, it's the same thing. The nitrogen is full, -3. The aluminum is +3. So essentially, you will have a huge potential energy difference between them. And basically, they measured them experimentally. Okay, so again, I want you to understand the lattice energy as how that is measured based on my talking about the concepts. Now, is it possible to memorize all this stuff? Sure it is, but it's much better if you understand it. And that's why I'm describing it in this way, so you can understand where the numbers come from.
Dr. Douglas.
Yes.
So with the Q plus and Q minus, are we like?
That's the charge of the species. Yes, that's the charge of each ion. Like the Q plus is like the sodium ion.
Okay, so it's the charge. Are you multiplying it by the charge of the Q minus?
Yeah, and that would be in coulombs. But you really don't know what coulombs are. But the point is, again, this is like the sodium ion there. And then you add the next one. This would be like the chlorine minus. So that's a charge on that. But again, I'm going to put 8 around the chlorine just for practice, because I think it's very important for you to fill it in and put the Lewis dot structure there to do that. Okay, so basically the charge is related to that. And then the K is the constant. The R is the distance between the ions from the center. And then the K is a constant associated with that. Yes.
So they have a positive 3 charge, negative 3 charge, and both charges.
Yes. Right. And they're in coulombs. So they'll be, they'll essentially,
9 coulombs.
yeah, something like that, whatever the, something times 10 to the minus 19 or whatever. But again, that's just a number that you calculate. That's what physical chemists get into, okay? And I'm an organic polymer thing, so I'm in the I don't care category, okay? But you going to biology, you're not going to care either. But it's important to practice the math so you understand at least where we're going with this.
Dr. Douglas.
Yeah.
You said K was a constant. Is that going to be given to us like in the problem?
Yes, of course.
Okay.
Yeah, and we'll talk about that in a minute. And the K is determined by experimental purposes usually. Like say, for example, magnesium and fluorine. And let's draw the Lewis dot structure for this. What do you suppose that's going to look like? Well, magnesium starts with this, right? With 1 dot there and 1 dot there. Now, let's be obvious about this. Where are the fluorines going to go? Think logically. The fluorines, they're going to naturally want to repel each other. Where are they going to attach to the magnesium? Yeah, on the side. So you put them over here. Fluorine, put 7 on it, right there. And then the other fluorine over here. Okay? Exchange the electrons. What are you going to do? Well, put the arrow in there. This goes there. This goes there. The result is now you have Mg plus 2 with the fluorine on one side that's -1 and the fluorine on the other side that's -1. Again, pardon my art, but I think you get the point. Yeah, someone had a question there. Anybody have a question virtually? I thought I heard a peep. Okay, but then with oxygen, you got the magnesium here, which is a +2, and the oxygen next to it, which is a -2. And I've got a question for you. Why is this a higher number? The charge difference is higher. You got a 4 + 4 charge difference, whereas the other one are like 2, and then another one that's a little less than that because this fluorine on this side, the fluorine on this side doesn't really notice. They just notice everything on the left, the magnesium and the one fluorine on the left. So the charge difference will be a little different. So they're not exactly additive. Yeah. So Brandon, you had a question?
No, sir, I didn't.
Oh, okay. Someone on virtual sounded something. Okay. So basically, that's the nature of how this works. Now I'm going to get my bad art off there again. Yeah, page. For magnesium fluoride? Well, basically, the charge difference would be the magnesium is +2 and the fluorine is -1, and then another one over there -1. So basically, the charge difference will be a little different because when it has this one connected, this fluorine connected to that, what is everything to the left going to be? What's the charge of everything to the left of the fluorine? No, +2 and -1 will be +1, right? Here, let me make it bigger. You got a fluorine here minus, and then you got the manganese +2. And let's put brackets around that to represent. The whole thing there will be -1 +2. So the whole thing is essentially going to be -1. And then over here, oh no, +1. And then over here it'll be -1. So the charge difference there is like 2. That's why these numbers that's why this number is lower than that number. Because they're not really additive, yeah.
So the less ions, the better, in terms of the higher charge.
Correct. Now, which do you think is more soluble in water, magnesium oxide or magnesium fluoride? Why? Yeah, very good, very good. Magnesium fluoride dissolves really easily in water. Magnesium oxide takes a little more effort, but it will dissolve. But that's related to dissolving because the water molecules do the pulling away because you got a positive region and a negative region for the water molecules. And we'll talk about that later. Okay. So lattice energy is important there. The +2 charge there regarded to both of them. The Q's there are given. Lithium fluoride there. Why is lithium fluoride stronger than lithium chloride? Be logical. Yes, very good. What's going to be a smaller radius? You look on the periodic table for the periodic trends we talked about before. The fluorine is going to be relatively small compared to the chloride. Okay, the chloride is going to be huge compared to the fluoride. So basically, the connection between the lithium fluoride there will be things. So what do you think is easier to dissolve in water, lithium fluoride or lithium chloride? Huh? The chloride, and it's even more the case with hydrogen fluoride. Hydrogen fluoride is considered a weak acid, but hydrogen chloride is considered a strong acid. Why? Why is hydrogen fluoride considered a weak acid? Well, because it likes to stay in one piece. It has a very strong bond strength between the hydrogen and the fluorine because that is H+ and the fluoride is F-. Okay, so they all work together with that. The lattice.
Dr. Douglas,
Yes.
so why does lithium fluoride Why is it just because the radius is bigger?
Yes, correct.
But how do you know that?
No. The lithium fluoride, the radius is smaller because you've got a small little ball here and a small little ball there. That's bigger there. But this one, the lithium is there, and then the chlorine is larger. So this radius will be smaller than this radius. Okay. Because this is on the third shell. This is n equals 3. This is n equals 2. Did that answer your question, Brandon?
Yes, sir.
Okay. So basically the Born-Haber cycle, that's just interesting. That's how they determine the numbers. And then there's a whole bunch of examples of different lattice energies there regarding that. And it's also related to the melting point, so we'll talk about that later. And then chemistry in action there with that, okay? So that kind of illustrates the bond, and I'll talk about this again next time, but we haven't talked about energy yet. This comes up in a later chapter. So we're all done. Are there any final questions, those of you virtual? Okay, we're done for the day. Have a good day, everybody. Please email me if you have any questions. I will have virtual office hours today. Yes.
So, just a question for lab tomorrow.
Yeah.
So I finished out filling in the non-metals portion.
Right, and
we're
we'll be doing the
metals.
metals portion, which just takes 10 minutes.
And we're also doing the color.
We're doing the color, and there's a video of that showing how to use the instrument, and you're just gonna put the thing in there and push the button and write down the to max and see the curve. That's it.
And group 2 is at 220 or
Yeah,
205,
yeah,
something like that?
yeah, and basically the timing is given there, and
But once we do it, we also have a week to write the.
yeah, and you'll
before
write
turning it
both.
in.
You'll just fill out both sheets, and that'll be the lab report.
Okay.
Okay? Yeah.
Is there any way I can get my test back, my last test?
For the lab?
No, for this class, the one that we took before. we took one.
Yeah, I did pass them back there, but I can. It's in my office. I'll give it to you.
Okay, can I?
Yeah, just wait a minute. Yeah,
Okay.
I'll gotta end this and shut things down.